Hey, we are live. Excellent, excellent, excellent. So, root, mean, square. Okay. So for this one, we are going to be talking about the speed at which gas particles move, usually molecules. So we have two charts here. Over here on the left, we are looking at the change in speed for our molecules based on temperature. Okay. So this red line is for the cold gas at negative 100 degrees Celsius. Really, as soon as I start recording, you jump up on my desk. Is that what's going on, little man? Okay. This green line is room temperature, 20 degrees Celsius, and this blue line is high temperature, 600 degrees Celsius. So the y-axis tells you how many molecules are moving at a particular speed, and the x-axis is the speed they're moving at. So the cold temperature, you have the peak at a much lower speed. The particles are just moving that much slower. As the temperature goes up, the peak speed is moving to the right. So the particles are moving faster and faster. So the average speed is getting higher and higher. Okay, so these represent distributions, where different temperatures mean that you're getting different speeds. You still get really slow molecules at high temperatures, and you're still going to get fast molecules at low temperatures. But you get a broader range of distribution at higher temperatures, and the average is going to be higher. Now, over here on the right, we see a similar sort of thing, only instead of looking at different temperatures, we're looking at different substances. Okay? So based on the mass of the gas particles, they're going to move at different speeds. So hydrogen is the lightest gas. It has the highest average speed. You can see its peak is way over here. Helium is a little heavier, so its peak is over here, so it's moving slower. Water is heavier still, so its peak is further to the left. It's slower. Nitrogen is even slower, and then oxygen is even slower than that. Okay. This is because kinetic energy is 1/2 mv squared. So at the same temperature, you are going to have different speeds for these different substances. Okay, because they have the same energy, the same average kinetic energy, but average energy is going to be modulated by mass. So heavier particles move slower. Speed is also proportional to temperature, okay? Meaning that higher temperature gives you higher speeds. Now, a couple of things. First up, we're really going to be talking about average speed rather than distributions. And really, we're talking about molar mass rather than the mass of the particle in question. Okay? And there's going to be square roots all over the place because of this guy, the 1/2 mv squared. Okay. So let's do a little bit of algebra. Not that much. For 1 mole of gas, the kinetic energy is 3/2 RT. Remember R, the universal gas constant. It's also equal to 1/2 mu squared. We're using u here because instead of just talking about speed, we're talking about the average speed. So we use u just for reasons. Now, for 1 particle, the kinetic energy is 3/2 RT divided by Avogadro's number because, we're converting from moles to particles. All right, but it's still going to be 1/2 mu squared. So you rearrange slightly. We're starting to do algebra. Multiply both sides by 2 to get rid of the fractions, and you have mu squared is equal to 3RT over Avogadro's number. Divide both sides by mass, you get 3RT over m times Avogadro's number. Now, the thing is, the mass of the particle times Avogadro's number gives you the molar mass. So once you take the square root, you get the square root of 3RT divided by molar mass. So what is this telling us? Don't worry too much about the math. What matters is that at higher temperatures, okay, you're going to get faster particles, and heavier particles or heavier gases, heavier molar masses are going to move slower. So higher temperatures mean faster particles. But because we're looking at a square root, 4 times the temperature, you get twice the average speed. 9 times the temperature, you get 3 times the average speed. Okay. So it doesn't go up linearly, this speed. It goes up with the square root. Heavier particles also mean slower particles. Okay? But again, we're looking at a square root. And we are also, because we're dividing, it's going to go down. So 4 times heavier means half the speed. 9 times heavier means 1/3 the speed. So one of the direct consequences, there are several, one of the consequences of this is that this means that gases explore space at different rates. Okay? So the two things we look at here are diffusion and effusion. Diffusion is when you have gas just expanding out into a volume. Okay? So like if you open up a thing of perfume in one corner of the room, it will diffuse throughout the entire room. Okay. Effusion is when a gas moves from one area to another through a small hole. Okay, so this is like a gas hissing out of a punctured tire. Or this is why your balloon eventually stops floating, because the helium inside manages to effuse through microscopic pores in the latex of the balloon, and oxygen, well, just air generally, will effuse into the balloon. All right, so what this means is that a heavier particle will diffuse or effuse slower than a lighter particle. So they'll also diffuse or effuse faster at higher temperatures. And again, it's going to be 4 times the temperature, twice the speed, so it'll diffuse or effuse twice as fast. But if your particle is 4 times heavier, then it will diffuse or effuse at half the speed. Okay. So different gases, different rates of effusion or diffusion will be based upon that same thing. So U, average speed, is equal to 3RT, the square root of 3RT over molar mass. This is known as Graham's law. Thank you for the noise, pup. Graham's law. The rate of effusion or diffusion is inversely proportional to the square root of the molar mass. Okay? Meaning heavier particles will effuse or diffuse at slower rates. So let's compare hydrogen and oxygen. Which one will diffuse or effuse faster, and how much faster? Okay? So for that, we pop over to our periodic table. Hydrogen has a molar mass of about 2, because remember, we're talking about diatomic elements. Right? Oxygen has a molar mass of about 32. Okay? So oxygen is 16 times heavier than hydrogen. Therefore, it's going to be slower. Okay? In fact, it's going to be the square root of 16 times slower. Okay? Meaning hydrogen will effuse or diffuse 4 times faster than oxygen will. Oxygen will diffuse or effuse at 1/4 the speed of hydrogen because it's 16 times heavier. Okay. So this is perfect fodder for a whatchamathing, a test question. Just, I mean, it could be simple, which one will diffuse or effuse faster or slower, or they could actually ask you for the number, in which case you would have to use the periodic table. You would have to find the molar masses, and from there you would have to just take the square root and that of how many times heavier. They won't ask you to calculate the average speed, probably. I mean, they could. It's just the square root of 3RT over m. But more likely, they'll ask you to compare two gases based on their molar masses. So the heavier one will move slower, and it'll be the square root of the difference. How many times heavier it is. All right. So that is root mean square, the root mean square law. Root, because we're talking about a square root. Mean, because we're talking about averages, so the average for U, and square, because, again, square root. All right. I'll be back in a few minutes to finish up Chapter 9 by talking about real gases versus ideal gases.